Our next section introduces the concept of conditional probability, and then based on that, we'll add another rule to our probability tool belt, something known as the multiplication rule. But let's first dig in and talk about this idea of conditional probability. So the notion is based on the following principle. Sometimes when you want to calculate a probability, you're actually able to obtain some additional information which should factor into your calculation. And the way that information factors in is it limits the possible outcomes in the experiment. So if we change the set of possible outcomes, that obviously impacts the probability. And here's a simple example. Let's say we're just looking at rolling a single die, and I ask you, what is the probability of rolling a 3? Well, you know what the outcomes are. The outcomes are the numbers 1 through 6. And so one of the outcomes corresponds to the event rolling a 3, and therefore the probability is 1 in 6. But now someone comes along and they say, well, I already performed this experiment. I'm not telling you what happened on that roll, but I am telling you that I rolled an even number. So when we were just looking at rolling the die, the outcomes were 1, 2, 3, 4, 5, 6. If someone says, oh, well, we actually rolled an even number, then the only outcomes are 2, 4, and 6. So you can see how this additional information has limited the outcomes that are possible in the experiment. Because now, if I'm just limiting my attention to this new smaller set of outcomes, what now is the probability that I roll a 3? The probability is now 0 because 3 is not an outcome that is in this new set. So adding some information changed the probability. And this is what conditioning or conditional probability does. It limits the number of possible outcomes, and that may result, it's not guaranteed to result, but it may result in a change of probability. So we have special notation for this. If we are interested in the probability of event B, and we are given a piece of information that says event A has already occurred, then the way we denote that conditional probability, we still use a big P for probability. The event that we're interested, B, we write that first, and then we use a vertical line to denote conditioning, and the piece of information that we're conditioning on, we write after that line. So the expression you're seeing here that I put in the red box, that reads probability of event B given that event A has taken place. So that line reads as the word given. So we're still interested here in the probability of B, but we're adding extra information by taking event A into account, and this will potentially limit the outcomes that are relevant to our calculation. Now, next point here is a fairly technical one, but I'll dig a little deeper. When we discuss conditional probability, and also the notion of independence, which we'll get to later in this section, we will assume that the event that is given, so in this case, in our formula A, has a probability greater than 0. And all this means is that we are not trying to condition on something that is impossible. The conditioning actually provides us with extra information because it has a non-zero probability. And what do I mean by we're not conditioning on something that is impossible? Say I'm rolling a standard 6-sided die. It would be valid to condition on saying the die roll was a multiple of 3. If I say it's a multiple of 3, the possible outcomes are 3 and 6, right? Therefore, that has to be valid because I can write down a set of outcomes corresponding to what I'm conditioning on. But what if I try to say that I'm conditioning on a die roll being a multiple of 10? Which of the numbers 1 through 6 is a multiple of 10? None of them. So here I'm trying to condition on something that is impossible in my experiment, and so clearly that's not a valid conditioning. The probability here that I roll a multiple of 10 is 0. And anytime a probability is 0, it's not valid to condition on that. So that's what it means here when I add this technical condition that the given event has a probability greater than 0. I'm not trying to condition on something that is impossible. So let's look at an example here of how conditioning plays out. Say we're looking at a college class that has 16 students. 10 of the students are women, 6 of the students are men. We also know that 4 of the women are seniors and 3 of the men are seniors. So the first probability I want to calculate is just that a randomly selected student is a senior. So there's no conditioning here. I'm just looking at all the students. So how many students are there in total? There are 16. And how many of them are seniors? Well, 4 of the women and 3 of the men, so 7 in total. And so the probability that a randomly selected student is a senior will be 7 over 16 as a fraction. And if you were converting this to a decimal and rounding, well, not even rounding, this just to 4 decimal places is 0.4375. So probability that a randomly selected student in this class is a senior is 0.4375. Now let's stick with the same example. Still want to calculate the probability that a randomly selected student is a senior, but now I'm conditioning on, I'm being given that the student is a woman. So how many students in total are there that are women? We know there are 10. And how many seniors are there that are women? Well, 4. So the probability that a randomly selected student is a senior, if I already know the student is a woman, is going to be 4 in 10 or 0.4. So you can see by adding the information, knowing that the student is a woman, my probability changed. Without the conditioning, it was 0.4375. With the conditioning, it's 0.4. So I added an extra bit of information. In the first example, we didn't know anything about the gender of the student. In the second example, we are being given information about the gender, but that changes the outcomes that are possible. There are no longer 16 possible students we can choose from. There are only 10 possible students that satisfy this additional criterion. And there are only 4 of them that are seniors, as opposed to looking at the total number of seniors in the class. So, if we want to generalize this notion, the principle is, if we are given that event A has occurred, then the only possible outcomes that we have to consider are those that are already inside event A. And so if I then want to calculate the probability that B occurs with this conditioning in place, then the only relevant outcomes are the ones that are in both events A and B. And it's useful to visualize this with a Venn diagram. I have two events here, A and B. I am, and let's visualize, we have all these different outcomes for the experiment. And so when I condition on A taking place, given that A has occurred, that means I am now restricting my attention only to event A. And so if I now want to calculate the probability of B, the only part of B that is left is what exists here where A and B overlap. So only the events that are in both A and B, those are the relevant ones in B that I still care about. So one way to calculate this probability of B given A, is I go and count the number of outcomes that are in both A and B, so they exist in that overlap or that intersection, and I divide by the number of outcomes that are only in A. And we can introduce some mathematical shorthand here, just to make the formula more compact. We can write lowercase n of A to denote the number of outcomes that are only in event A. And we can write lowercase n and then A and B in parentheses, and we let that denote the number of outcomes in both A and B. So our conditional probability formula, probability of B given A, is now given by n of A and B divided by n of A. Number of outcomes in A and B divided by number of outcomes in A. And this is useful when you are able to count outcomes. We'll see in a minute, we don't always have the ability to count outcomes. And also, the outcomes are all equally likely. So let's look at another example. The US Senate voted to confirm Elena Kagan to the Supreme Court in August of 2010. The table here shows us the breakdown of votes by party affiliation. Now, first probability we want to calculate is just the probability that a random senator voted yes. So how many senators are there in total? 100. How many yes votes were there? 63. So the probability that a random senator or randomly selected senator voted yes is 63 over 100, or 0.63. So there was no conditioning in this first part. We just said, if I take the 100 senators and I select one of them at random, how likely is it that senator voted yes? So party affiliation doesn't factor into this calculation at all. But now someone else says, oh, but perhaps party affiliation should be taken into account. I still want to know what the probability is that a random senator voted yes, but I don't care about all the senators. I'm just going to select a senator that's a Republican. So now I want to calculate how many senators in total are Republican. So I'm restricting my attention to the smaller set of outcomes, only looking at Republicans. And in this case, there are 41. And how many yes votes came from Republican senators? According to this table, only 5. So the probability that a randomly selected senator voted yes, given that the senator was Republican, is 5/41 as a fraction, or converting that to a decimal and rounding to 4 places, it's 0.1219. And so you can see how dramatically this probability changed by adding the extra information. When we were not looking at party affiliation, that was irrelevant. The probability was 63%. If we add this extra layer and we only look at Republicans, so we are conditioning on the senator being a Republican, the probability drops to just larger than 12%. So conditioning can have a really big impact on probabilities. And it shows you the value of, if you have additional relevant information, you should make use of that because it can dramatically impact probabilities. So what about if we are not able to count? What if we can't list the outcomes and we can't count how many are in A and how many are in A and B? Well, it's possible to express the conditional probability just in terms of probabilities. The probability of B given A can also be calculated as the ratio of the probability of A and B divided by just the probability of A. Formula looks exactly the same as before, where we had N instead of P. So if you are not able to count outcomes, but you do know probabilities for the individual events and for their overlap, you can still calculate a conditional probability. So counting isn't needed here. You can get around the counting. And the counting approach, as I mentioned, requires equally likely outcomes. When we're working with probabilities, that condition gets dropped. We don't have to worry about equally likely outcomes anymore. So let's look at an example. Suppose a poll of local voters indicates that 45% favor a property tax increase, 65% favor the establishment of a state lottery, and 12% favor both. Let's write down that information first. So probability that someone favors a property tax increase is 0.45. The probability that they favor a state lottery is 0.65. And the probability that they are in favor of both, so property tax increase and state lottery, is 0.12. Now we're being asked if a voter is in favor of a property tax increase. That word if, that's the key that we're conditioning. Whatever probability we're calculating, we are conditioning on someone favoring a property tax increase. If we know they favor a property tax increase, what is the probability that they also favor a state lottery? So what's the probability that they favor a state lottery given that they favor a property tax increase? And our formula says, remember, probability of B given A is equal to the probability of A and B divided by the probability of A. So if we match A and B to these statements, then this will be the probability of both property tax increase and state lottery divided by the probability that they favor a property tax increase. And you're always dividing by whatever it was that you're conditioning on, right? we're conditioning on A in this formula, and so we end up dividing by the probability of A. And let's plug in these numbers. The probability that they favor both is 0.12. The probability that they only favor a property tax increase is 0.45. And so we could express this as 12 over 45, and you could go and simplify that fraction. Or we can express it as a decimal rounded to 4 places, 0.2667. There we go. Now there's another useful application here. We can take that formula for conditional probability and we can rearrange it and solve for the quantity probability of A and B. So sometimes that's what we're interested in calculating, the probability that two different events occur. And if the conditional probability information is available to us, then rearranging the conditional probability formula is really useful. This rearranged formula we call the multiplication rule, and it says the probability of A and B is equal to the probability of A multiplied by the probability of B given A. So if you check, this is just the conditional probability rule, and I rearrange the terms and solve for the probability of both events happening. So it tells us if we know a conditional probability, in this case B given A, and we also know the probability of what we're conditioning on, A, and we multiply those two probabilities, it will give us the probability of the two events happening. So this is often really useful if you're thinking about events happening sequentially. For example, say I'm drawing two cards from a deck. There's going to be a first card that I draw, and then there's going to be a second card that I draw, right? So first card, second card. I want to know what the probability is that both cards are kings, which I can express as the first card is a king and the second card is a king. So I'm trying to find a probability of an AND statement. Now I can look at just the first card. If I have a standard deck of cards, what is the probability that a randomly selected card is a king? Well, how many kings are there in the deck? 4. And how many cards total are there? 52. So the probability that the first card is a king is equal to 4 over 52. Let's just leave it like that for now. Now I'm going to my second card, and now I want to condition. And what am I conditioning on? What happened on the first draw? I already drew a king. So on my second draw, how many kings are available for me to draw from? Only 3. And how many cards are there in total to draw from? 51, because that king that I drew was removed from the deck. So the probability that the second card is a king, given or conditional on the first card being a king, is 3 over 51. Now I have my one probability for the first event. I have the probability for the second event conditional on the first. Like I applied that conditioning. And so the probability of the AND statement that both are kings is the product of the two probabilities, 4 over 52 multiplied by 3 over 51. And this is 12 over 2652. And if I go and express that as a decimal and round to 4 decimal places, it's 0.0045. What's really cool about the multiplication rule is you can extend it beyond 2 events without having to think about it too much, as long as you can apply things sequentially. So let's stick with the deck of cards example, and I'm going to draw 3 cards now, and I want to know what is the probability that all 3 cards are spades. So I want the probability that the first card is a spade, and the second is a spade, and the third is a spade. Right. There's a first event, a second event, a third event. So let's look at those in sequence. When I draw my first card, there are how many spades in total? 13. And there are a total of 52 cards. So the probability in this case is 13 over 52. Now I go to my second draw, and I have to carry the conditioning forward, right? I have to take into account the fact that I drew 1 card and it was a spade. So how many spades are now left in the deck? 12. And how many total cards are left in the deck? 51. So this probability is 12 over 51. And then I move on to my third draw. And again, I have to carry this conditioning forward. I have to carry all of it forward now. How many spades have I drawn already? 2. So how many spades are left in the deck? 11. And how many cards total are left in the deck? 50. So this third draw has a probability of 11 over 50. And I multiply all 3 of these probabilities together. Let's see what that gives us. 13 times 12 times 11 is 1716. And the 52 times 51 times 50 is 132,600. And let's convert this to a decimal and round to 4 places. This will be approximately 0.0129 or 1.29%. So really small probability, not impossible, but just larger than 1%, the probability that 3 random cards drawn in a row are all spades. And I hope the idea here of sequential conditioning helps. Like, you just think, if I perform these actions in sequence, how does the first action affect what's possible on the second? How does the second action now affect what's possible on the third? And you just do those in sequence. Now, sometimes, even if events play out in sequence, it's the case that one of them has no effect on what happens next. In the case of drawing cards, like, clearly there's a downstream effect. If I draw a spade now, it's not in the deck to be drawn later. So what happens now affects what's possible later. On the other hand, if you think of something like flipping a coin, say I flip a coin twice. I see heads, flip it again, see heads again. The first coin toss in no way affects what is possible on the second coin toss. So even if I know the first coin toss was heads, it's not going to affect the probability of the second coin toss coming up heads. That probability will still be 1/2. And so we say these 2 events are independent of one another. We can formalize this a little bit. If we have 2 events, A and B, and they are independent of one another, then if we know they are independent, mathematically, that means conditioning has no effect. So if I'm calculating the probability of B and I'm conditioning on A, that conditioning is irrelevant. Probability of B given A is just equal to the probability of B. Conditioning did nothing. And I can flip that around. Probability of A given B is equal to the probability of A. In fact, if one of those statements is true, then the other statement will also be true. So independence means both of these statements are true. And if you have only that one of those statements are true, it tells you the other one is true as well. And this can also have an impact on the multiplication rule we looked at earlier. Remember, the general multiplication rule said the probability of B given A is equal to, the probability of A and B is equal to the probability of A multiplied by the probability of B given A. Well, if we have independence, this probability of B given A is just equal to the probability of A if we have independence. Probability of B. And so that means the probability of A and B is now just the product or just the multiplication of the two individual probabilities, P of A times P of B. And let's look at a quick example of that. Suppose the probability of rain on a particular day is 56%. And the probability of your favorite basketball team losing is 3/5. What is the probability that you will have a particularly bad day with both rain falling and your favorite team losing? You may assume rain falling is independent of how your favorite basketball team performs. So because we have independence, we know the probability of it raining and your team losing is just given by the probability of raining multiplied by the probability of your team losing. And what were these respective probabilities? The probability of rain was 0.56, and the probability of your team losing was 3/5, which you can go and check is equal to 0.6. So if I multiply these two probabilities, then I get probability of 0.336, or a 33.6% chance that both of these things happen to you on the same day. So I know there's a lot to take in this lecture, and we will do plenty of examples tomorrow, but maybe it's even helpful to watch this a second time, and I will see you online when we do examples.